Okay, so let us begin. We are going to begin once again with the recap. It is going to be a rather long recap. I want to mention quite a few things in this recap. So, the general theme that we have been following in the last few lectures is soft decoding. Okay, so in particular we saw two different optimal soft decoders. If you want to look at optimal soft decoders, there are two possibilities. One is the ML decoder, right? The other is the bitwise MAP decoder. Okay, and so soft decoding we've been always we'll always assume BPSK over AWGN. Okay, so keep this in mind. So BPSK will be -1 + 1, and AWGN is noise 0 mean variance sigma squared. Okay, all these things will be underlying assumptions that I may not repeat every time, but that's the idea here. So for some reason okay, let's come back. Okay, so now we have some good descriptions for the ML decoder and the bitwise MAP decoder. Okay, so the ML decoder is quite easy to describe for BPSK AWGN. Okay, you have to do something which is very simple. What do you have to do for the ML decoder? Suppose you have a received vector R1, R2, Rn. You have to compute correlations. Okay, so how many correlations do you have to compute? So if the code is okay, so for some reason it thinks I am doing something here with the okay, so I don't know how to avoid that. Sorry?
Hide the toolbar.
How do I hide it?
Just right click and
click there. Toolbar. Properties. Auto hide the taskbar. Is that okay? So what do I do? Okay, let's try auto hide and see what happens. Oh my god. Apply. Okay. So it seems a little bit better. Okay. All right. So what do you do with the received vector R if you were to do ML decoding? You have to compute correlations. What are the correlations you have to compute? You have to do R dot 1 minus 2U, right? So what is this U? You have to maximize over all U in the code. Okay. So that particular code word which gives you the maximum correlation you pick as the ML decoded code word, and that will give you good properties. For the bitwise MAP there are various descriptions possible. We finally settled on this likelihood ratio description, okay, which was at least there was a conceptual advantage in that. Okay, so there was no computational advantage. Even in the ML decoder there is no computational advantage in changing anything, because the reason why, I mean, you still have to do 2 power k correlations. Okay, so that's a lot of correlations. You can't really do it if k becomes large. Okay, same thing is true in the bitwise MAP, but with the likelihood ratio at least there is a conceptual understanding of how the final expression splits into some convenient parts, and that's useful. Okay, so I think if I remember right, I called capital Li, right? Did I use capital Li for the final probability that the bit is 0 given R divided by probability that the bit is 1 given R. Okay, so there is a way to convert this into likelihoods, because if you assume that your code is non-trivial in every location, you will get a very simple conversion into likelihoods, and if you do a lot of simplifications you can write it as Li. Okay, what is Li? This is basically probability that Ci is 0. Oh no, I think I should write it in terms of f. Okay, so that's better. f of Ri given Ci equal to 0 divided by f of Ri given Ci equal to 1, okay, which will simply be e power 2r by sigma squared, right. So, I think there was also a log likelihood ratio. Did I mean I must have introduced that. So, did I say log of this was capital Li? Okay. So, nobody objected to that. Okay. Okay. So, small li is also log of that, right? Is it log of that? Okay. So, I think that's a better thing to work with, because you will see there are some simple advantages there. Okay. So, log of this, which works out to 2 Ri by sigma square. Okay. So, you can write this as small li plus an extrinsic term. The extrinsic term is a bit messy. Okay. So, I am not going to try and reproduce it. The extrinsic term is messy and it involves a numerator and a denominator. The numerator is contributed by those code words which have 0 in the ith position, and the denominator is contributed by those code words which have a 1 in the ith position. You have this trick of dividing every term by something and then writing it up in some convenient form. And finally, if capital Li is, so basically the decision on the ith bit, which I think we called as Bi maybe. Okay, so the Bi, which is the decision on the ith bit. Okay, this is basically 0 if Li is greater than 0. It's 1 if Li is, let us say, less than or equal to 0, it does not matter. Okay. So, this is the final decision, remember that this is the final decision. Okay, in a bitwise MAP. Alright, so this is a brief recap of what we did, but the main observation is both of them are roughly 2 power k complex, okay, where k is the dimension of the code. Okay, so, if n code is an nk code, and if k is increasing, k becomes 1000 and all that, you have no hope of implementing either the optimal ML decoder or the optimal bitwise MAP decoder completely. Okay. But this form for the bitwise MAP decoder is interesting, as in it suggests that you might be able to either iteratively or approximately evaluate the extrinsic term, maybe even wrongly. When I say approximately, I mean wrongly, maybe even wrongly, but there also there might be some advantage. Okay. So, suboptimal soft decoders are what is, those are the decoders that are really interesting. Okay. So, you are not really interested in optimal soft decoders, because in most cases they are not implementable. So, suboptimal decoders are going to be crucial. Okay. So, that is the main idea here. So, the main reason you study optimal decoders is not to implement them, it is to realize that suboptimal decoders are needed. Okay. So, that is the reason why you study optimal decoders here. Okay. So, what do you do for suboptimal is an interesting question. Yes. Okay. So, optimal for what? So, whenever you say optimal, you mean it has to minimize or maximize something, right. So, the ML decoder will minimize the probability of block error. The bitwise MAP decoder will minimize the probability of bit error. Okay. And both of them are the same. In fact, what happens is, if you simulate either one of them, you will see one will lie on top of the other. Okay. Both will be exactly the same in most cases. So, you do not have to worry too much about it, but they are strictly not equivalent. Okay. That is one point. So, another comment I want to make, which was raised I think towards the end of maybe the last lecture, is about error correcting capability for these optimal decoders. Okay. So, if you remember on the BSc, we saw syndrome decoder, etc., and then we defined a notion of an error correcting capability for a decoder, and then in fact we even had a bounded distance decoder which works only within a certain radius, right. So, only if there are lesser than so many errors you can correct it. Okay. What about the soft ML decoder for BPSK AWGN? What is its error correcting capability in the sense that we defined before? Okay. If there is one error, can it correct it? If there is 2 errors, can it correct it? That is the kind of question I am asking. Okay. So, let us say we take the repetition code. Okay. And if I ask you the question, what is the error correcting capability for the ML decoder, what will the answer be?
n minus 1 by 2.
So think about it. So what should happen if error correcting capability? So let's say we fix the 3,1 repetition code. Okay, and then I use it on the BPSK AWGN just like before. Okay, all right, didn't like it, still doesn't like it. Okay, AWGN, we are using BPSK over AWGN, and then we are asking the question, what is the error correcting capability? What are we using? We are using the soft ML decoder. What does the soft ML decoder do? It evaluates R1 plus R2 plus R3. If this is greater than 0, it decides the transmitted bit was 0. Okay, if it is less than 0, it decides the transmitted bit is well, the code word, let me say code word, because error correcting capability is defined with respect to the number of errors in the code word, right. So the code word was 000. In this case, it decides the code word is 111. Okay. So when you define error correcting capability, you need this notion of number of errors. Okay. It does not make too much sense in BPSK AWGN, you will see why, but number of errors is something that we used in BSc. Okay. So when do you say what about R1, R2, R3? What is the number of errors in R1, R2, R3? Suppose you are transmitting 000, what is the notion of number of errors in R1, R2, R3? What is one way to define it, for instance? If you want to define it like in the BSc sense, how would you define it? Yeah, take the sign. So you are doing some kind of hard decision and saying, suppose I say if Ri is positive, I will say no error happened in the transmission of the ith bit. If Ri is negative, I will say some one error happened. Okay. Suppose you define number of errors in that sense. Okay. What is the error correcting capability of the soft ML decoder? Okay, so I have to define number of errors is the size of Ri such that Ri is, let us say, less than 0. Okay, remember I am transmitting the all 0 code word that I have fixed. Okay, I fixed the all 0 code word, and then I am saying number of errors I am defining as the number of positions where Ri is negative. Okay. So if I do this, in fact the soft ML decoder has no error correcting capability. There are R1, R2, R3 for which it will make an error. I mean, so right, do you see that or not? Suppose if R1 is 0.1, R2 is 0.1, R3 is minus 1.1. Okay. Technically there is only one error, but then your soft ML decoder is going to wrongly decode to 111. Okay, right. So remember, why did we ask that question of error correcting capability in the BSc? Why was it so important? Why did it make sense? Okay, it made sense because lower weight errors were more probable always. Okay, only the number of errors mattered in the probability. Number of bit errors mattered in the probability of the entire vector. Okay. Now when you go from 000 to R1, R2, R3, number of errors does not make much sense. Okay. So for instance, you might say I transmitted 000 and I received, let us say 0.1, 0.1, I do not know, minus 1.5. Okay. Or you might say I transmitted 000 and I received 0.9, let us say 0.8 and then minus 0.1. Okay. Now both these guys from an error correcting capability point of view are thought of as being the same, right. You do not see a difference between these two guys, but then this one is much more probable than this guy. Okay, so this is more probable than the previous one. Okay. So asking questions in terms of error correcting capabilities for soft decoders is not entirely correct. You should not worry about it. Okay. The fundamental principle there, the reason why we asked for error correcting capability in BCH in the BSc was lower weight errors are more likely always, and so we asked that question. Okay. Here the only question you should ask is what is the probability of error. Okay, what are the more likely errors? The more likely errors are corrected by the soft ML decoder, that is all. Whatever the ML decoder corrects is the best possible thing you can do. Okay. So in general for soft decoders, questions like error correcting capability are seldom asked. Okay, it is tough to answer that question. Okay, it is not very easy entirely, you cannot answer that question. Okay, so people do not worry about error correcting capability, you only worry about probability of error. Probability of error is lower, you are happy.
So what about when it is low SNR domain? You can see that even larger vectors are more probable that time, right?
Well, then even if you whatever SNR you pick, something like this, the vector below will be more probable than that vector. That's what I'm trying to say. Okay, it's not that dependent on SNR. But it's true, I mean when you go to and the opposite is true when you go to high SNRs. Actually where it really hurts is when you go to really high SNR, you would like to have a guarantee on error correcting capability, because at high SNRs you can say number of errors are going to be low. That you can say, but you can't say the opposite. That's what I'm saying. Particularly at lower SNR, comparing two vectors much more difficult. Okay. All right. So that's just a point of departure. I wanted to point that out because somebody asked me that question, I think towards the end of last class. I wanted to reiterate that. So in general, you should not ask this question for soft decoders. Don't worry about number of corrected errors. Okay, only at high SNRs you have to worry about it, but that's something we'll come back to maybe later if we have time. Slightly more difficult notion to get your head around. Okay. All right. So that's that. Okay, so what we are going to see next is just this one more thing about the bitwise MAP decoder. After that, we will move on to something little bit different. Okay, so I will call this as the dual implementation of bitwise MAP. Decoder. Okay, so this is a crucial idea. Okay, so this plays a fundamental role in the simplification of this of at least one kind of suboptimal decoder. Okay, so that's the idea here. Okay, so I'm going to do this once again by example. There are general expressions, and this idea is basically due to two people called Hartman and Rudolph. I'll encourage you to read their original paper. It's not too difficult to read. Okay, so they are the ones who introduced this idea of looking at the dual code to implement the bitwise MAP decoder for the original code. Okay, so far the bitwise MAP decoder was implemented using the code words of the original code itself. Okay, now when you go to higher and higher data rates, what will happen? When k by n increases, what happens? Your dual code will have much fewer code words than the original code. Okay, so if you have a bitwise MAP decoder described in terms of the code words of the dual, you have a computational advantage. Okay, it may not be a huge advantage, but at least there will be something. Okay, so this is kind of similar to the syndrome decoder. So if you remember when we motivated the syndrome decoder, there also something very similar happens. Complexity is really 2 power n minus k, it's not 2 power k. Okay, even though it's suboptimal ML. Okay, so this is kind of reminiscent of that idea. Okay, so instead of using the generator matrix for the decoding, you're going to use the parity check matrix. Okay, so I'll do this once again by example. We'll do a couple of examples and see cases where it works, cases where it doesn't work, and then we'll just leave it there. Okay, so without going much deeper into the technical details. Okay. Okay, so for some reason this thinks whenever I put my hand down, it thinks I'm writing something there. That's the problem, I think. The touchpad technology doesn't distinguish between my hand and the pens. Maybe there is some setting that you can do to make that happen. I don't know. Anyway, so let's take the first example. The first example I'm going to take is let's make it a little bit non-trivial. We'll take the 4, yeah, 4 is fine. 4 comma, should I take the 4 comma? Okay, so we'll take 4 comma 3 even weight code. Okay. So, let me remind you what is the even weight code. What is the even weight code? Okay. So, it is basically the dual of the repetition code, that is another way of defining it. Okay. So, this is the dual of 4,1 repetition code. Okay. So, another way of describing the even weight code is to say that it contains all the length 4 binary vectors of even weight. There will be exactly 8 in number. So, it is a 4,3 code. You can also check that it is a valid code, etc., etc., all that you can do. Okay. So, let us see what are the various code words of this code. Okay. So, there will be 8 of them. 1 1 0 1 0 1 1 0 0 1, then what 0 1 1 0 1 1 0 0, then what 1 0 1 0, and then 1 1 1 1. Okay. So, those are the 8 code words of this code. Okay. Let us try and write down the expression for what? For capital L1. Okay, let us try to write this down. If you were to write the expression for capital L1, what would happen? Capital L1, remember, is the a posteriori likelihood log likelihood ratio for the first bit. Okay, so you will have a form similar to before. Okay, you will have 4 terms in the numerator and then 4 terms in the denominator. Yeah, all that is okay. So, BPSK over AWGN minus 1 plus 1, everything sigma squared, those things I am not going to repeat for every single situation, that is assumed. Okay. Okay, so it is basically going to be L1 plus what will be the extrinsic term? You have to take logarithm of these e power products, right. So, it is going to be e power, okay, so it is going to be e power L2 plus L3 plus L4 plus e power L2 plus e power L3 plus e power L4. Is that okay? Everyone agrees with the numerator? Okay, and then the denominator, you would have e power L2 plus L3, okay, L3 plus L4,
L2 plus L4,
L2 plus L4 plus 1. Is that okay? It should be a plus 1, which I can see. Of course, if you have not been keeping up with these lectures, you are suddenly happily relaxing for 2 weeks and showing up, this expression will be surprising to you, but I can't help that, you know. you have to keep up with the lectures. Okay. So, this is the expression. Okay. Any insight, anyone willing to, I mean, take a wild swing at it, see if you notice something here which you think is interesting? No, not really, right? I mean, I don't want a brilliant answer, you know? I just want a simple answer to say not really. I mean, it's not, doesn't seem very obvious, at least. Actually, there might be, but it doesn't seem very obvious that it should be it's some very illuminating answer. But on the other hand, I will describe the same code in a slightly different way, and then I will ask you the question about what is this capital L1 and how are we trying to find it, and you will see there should be a simpler explanation, and that is where this idea of using the dual comes in. Okay. So, let us see. So, if you look at the parity check matrix for this code, what is the parity check matrix? 4 ones in a row, right. So, that is the parity check matrix for this code, it is the dual of the repetition code. So, the generator matrix for the repetition code becomes the parity check matrix for this code. So, you have 1 1 1 1. Essentially this code is described by set of all code words C such that C1 plus C2 plus, okay, I will put a circle around plus because we are also dealing with real numbers here. So, I want to distinguish between plus and XOR. C1 XOR C2 XOR C3 XOR C4 equals 0. Okay. So, that is a complete description for the code. Code is the set of all code words C which XORs to 0. Okay. So, any dependency between the 4 bits of the code word is captured by this equation. In fact, any dependency between the 4 received values is captured by just this condition. Okay, so, this you better convince yourself of this because I am going to change this in a tricky fashion later and I will ask you the same question. It will seem like it is true, but then it will not be true. Okay. So, it is good to convince yourself that this is true. All dependencies are captured in this equation. Okay. So, that is the only condition that relates C1, C2, C3 and C4. There is no other condition that relates it, yes or no, right. For all code words this is the only condition. Okay. So, now if I ask you the question given R1, R2, R3, R4, what is R1, R2, R3, R4? You know how it is described, right. You can encode the code word, I mean you modulate the code word to +1 -1 and send it through a 4 independent realizations of the AWGN channel, you get 4 received values. Okay. So, given these 4 received values, the question I am asking when I compute capital L1 is what is logarithm of probability that C1 is 0 given R, okay, this is the vector R by the way, divided by probability that C1 is 1 given R. Is that okay? All right. So what? Okay. So, anything occurs to you now? So, if you can use this equation in some smart way to simplify this expression, okay, right, the answer you get clearly should be the same as the answer you had before. Okay. So, that was also some expression for the same probability. If you can now use this equation in a smart way to somehow simplify this probability, I am not saying how you would do it, but if you can do that, then the answer you get should also be the same. You should not suddenly you should not get anything that is drastically different or entirely different. So, this equation clearly captures everything and that is what we are going to use. Okay. Is that okay? So, let me describe that approach. It is not entirely different from what we have been seeing before, but you will see that the way we think about it will change. Okay. So, let me look at this again. So, I want to look at this question. I am given this equation C1 XOR C2 XOR C3 XOR C4 is 0. Okay. I am given a received vector R, which means probability that, so let us say I try and compute this probability that C1 is 0 given R1. Okay. This is for me easy to compute. So, let me not do this computation, let me just, okay. So let's look at this equation first and then ask the question what does, I mean how we can use this equation to simplify the previous expression. Okay. So, that is what I want to find out. So, I am going to approach this in a slightly different way. Suppose somebody tells me Pi is the probability that Ci is 0. suppose somebody tells me this, okay. Do not worry about how I got this answer. Somehow somebody tells me Pi is the probability that Ci is 0. So, of course, 1 minus Pi will be the probability that Ci is 1, okay. So, that is okay. Okay. And now from this equation, okay, I have, so suppose I rewrite this equation as C1 equals C2 XOR C3 XOR C4, okay, I can do that, okay. So, now I have one value P1 which tells me something about C1, okay. So, that is something that is given to me, and then this equation and the values P2, P3 and P4 will tell me something about C1 again, right, yes or no. Okay. So, if you try and compute what that expression is, it looks like you will get something a little bit complicated, but to compute that I will do that in 2 steps, okay, instead of computing everything totally. The first step I am going to ask is, suppose I have an equation of this form. Suppose I say x equals y XOR z, okay. So, we will try and use this information in a slightly different way, okay. Suppose I give you x equals y XOR z and Py is the probability that y is 1, let us say y is 0, it does not matter. Likewise here Pz is the probability that z is 0, okay. So, if you now try to compute probability that x is equal to 0, okay. So, you are going to get, yeah, so y and z both have to be either 0 or both have to be 1. So, you would get something like this, Py Pz plus 1 minus Py times 1 minus Pz. Yeah, assuming independent. So, let us say these are independent, okay. So, y and z independent. Is that okay? So, now this equation looks, so maybe this is I should call it something. So, let us say this is some P E x, okay. The reason why I put E is some kind of extrinsic information about x, okay. So, notice this does not use any intrinsic information I might have about x. If somebody told me ahead of time that Px was something that I had already, this information is new, okay. It kind of, it has to be in a way combined with the previous information I had, okay. So, we will see how to put it together in the decoding context later, but anyway, so this question is interesting, okay. So, this expression seems simple enough, but now if you try and use this here, see C2 XOR C3 XOR C4, you will see you will have many more terms, right. You have 4 terms and it does not seem like there is any simple way of simplifying it. The crucial trick is to look at this quantity. The quantity you have to look at is basically probability that x equal to 0 minus probability that x equal to 1, okay. If you look at this, it turns out this will become something like this. So, let me write this down more clearly. Probability that y is 0 minus probability that y is 1 times probability that z is 0 minus probability that z is 1, okay. So, it turns out in this equation x equal to y plus z, okay, this is true, okay. You are given only this guy and this guy. With only these 2 information, if you have to find anything about probability of x, if you go ahead and find that probability, this equation will be true, okay. So, you can simplify this. It does not seem very obvious from this equation, okay. Probability of x equal to 0 minus probability of x equal to 1, it does not seem very obvious from this, but you can simplify it and you can write it this way. So, if you want, I will quickly show you how that works out. Okay, let me quickly show you how that works out. Okay, for some reason I am not able to go there. So if this is extremely okay. So if you look at this expression, we try and evaluate it, it is going to be py pz plus 1 minus py 1 minus pz minus what, py into 1 minus pz minus pz into 1 minus py. Okay, if you simplify this, you will get this difference. Okay, remember what is this difference? It is 2 py. So this guy is what, py minus 1 minus py, right. So it is 2 py minus 1, and this is also 2 pz minus 1. Okay, so if you simplify this, you will get that. Okay, so you are getting 4 times py pz. You can see these two are the same. Okay, so it's an interesting simplification that happens. Okay, so if you have x equals y XOR z, and you are given only probabilities for y and z, and only using that if you want to compute probabilities for x, okay, it turns out this equation will follow this rule. Okay, probability that x equal to 0 minus probability that x equal to 1 will be the product of these two probabilities. Is it okay? So by itself this may not be so interesting, but when you convert it into log likelihood ratio, okay, by itself also it is interesting, by the way, but anyway, if you convert it into log likelihood ratios, it becomes even more interesting. Okay, so how do we convert this into log likelihood ratios? Okay, so the first important trick is to realize that you can divide anything you want by probability of x equal to 0 plus probability of x equal to 1. Why can you do that? It is always 1, so you can happily divide anything you want by that. Okay, so that will help you in this computation of probability. So let me do that. So if I do that, you will see probability of x equal to 0 minus probability of x equal to 1. Okay, so these seem like, I know, very basic elementary computations in probability, but do be patient with me, we will get somewhere at the end of this work. Okay, plus x equal to 1, this is probability of y equal to 0 minus probability of y equal to 1 divided by probability of, here I will do y equal to 0 plus probability of y equal to 1. Okay, so I should do that, this times, remember this times probability of z equal to 0 minus probability of z equal to 1 divided by probability of z equal to 0 plus probability of z equal to 1. Okay, so what is the next trick to get to likelihood ratios? Okay, so you have to divide numerator and denominator by probability of x equal to 1. Okay, then you get towards likelihood. Okay, so if you call, let us say, Lx as log of probability that x equal to 0 divided by probability that x equal to 1, okay, and similarly for Ly and Lz. Okay, if you do this, then it turns out you can write this same expression as e power Lx minus 1 divided by e power Lx plus 1 equals e power Ly minus 1 divided by e power Ly plus 1 times e power Lz minus 1 divided by e power Lz plus 1. Is it okay? Okay. All right. So we can now further do some simplification. For instance, you might notice that there is some kind of a tan hyperbolic hidden in this, right? I don't know if you can see that. What is tan hyperbolic of x? It's, yeah, so you can write it as, see, remember sin hyperbolic x is e power x minus e power minus x by 2, and cos hyperbolic x is e power x plus e power minus x by 2. So now if I divide the 2, I get tan hyperbolic x. Okay, so now that if you cross multiply by e power x or something, you will get e power 2x minus 1 by e power 2x plus 1. Okay, so this becomes tan hyperbolic of Lx by 2. Okay, this becomes tan hyperbolic of Ly by 2, this becomes tan hyperbolic of Lz by 2. So essentially what this says is, if you have an equation of the form x equals y XOR z, and then you are given probabilities for only y and z, from that if you compute a probability for x, okay, those three probabilities px, py and pz, remember this is some kind of an extrinsic probability for x, okay, for y and z somehow somebody tells you probability, using that you compute the probability for x. If you do that, those three probabilities follow the tan hyperbolic rule, it is called the tan hyperbolic rule, tan h rule, basically tan hyperbolic of the log likelihood ratio of x by 2 is equal to the tan hyperbolic of Ly by 2 times tan hyperbolic of Lz by 2. Okay. Now, why is this form better, any better than any of the previous forms that we have had? Okay. Remember, now if I go back to my equation, what is my original equation I started with? C1 equals C2 XOR C3 XOR C4. I have a received vector R1, R2, R3, R4. R1 is telling me something about C, that C1 that I can easily compute, like log likelihood ratios 2 R1 by sigma square, there is no problem. The trick was in the computing the extrinsic part. What are R2, R3 and R4 telling me about C1? Okay. Now anything they tell me should be through this equation. Okay. Now R2 tells me something about C2, I know that. R3 tells me something about C3 and R4 tells me something about C4. So somebody is giving me these three probabilities for C2, C3 and C4. Now I want to figure out the extrinsic probability that I get from these three probabilities about C1. Once I get that, that is going to be independent of anything I compute with R1. I can simply either add the LLRs or multiply the probabilities and get the final answer. Did that make sense? Okay. So that is the high level idea here. Okay. So now why is the tan h rule important in all this? So it turns out you can extend it very easily. Okay. So remember, if I have x equals y XOR z, I was able to do it. Now if it is y XOR z XOR w, still all I have to do is add another tan hyperbolic of Lw by 2. Okay. So that is the nice thing about the tan hyperbolic rule, it just extends very easily. Okay. After all, y XOR z is just another random variable which is binary, so simply keep extending this. Okay. So it turns out the extrinsic information about the bit 1. Okay. So remember, when I write capital L1, okay, how will I write capital L1? I can write it as small l1 plus the extrinsic information, and what is the only extrinsic information that is possible? That comes through this equation. And what is the extrinsic information that comes through this equation? That is the solution of this. So how will I write that? The way to write it is 2 times tan hyperbolic inverse of what? Tan hyperbolic L2 by 2 times tan hyperbolic L3 by 2 times tan hyperbolic L4 by 2. Is that okay? Seems good. So who is going to now verify that this expression is exactly equivalent to the previous expression we had? Remember, what is the previous expression we had? This was our previous expression, right? Okay, first of all, how many of you think that these two are equivalent?
The derivation is good enough.
It has to be. So you
No,
don't
the
have to
derivation
check.
is good enough.
Derivation is good enough. Oh yes, maybe it can be. Isn't the log disturbing you a little bit? No?
Inverse NH.
Yeah, so there is an inverse expression which can be written in terms of log. Okay, so think about that. Okay, the tan hyperbolic inverse, you can write it in terms of log tan. So there's a way to do that. Okay, so it's very similar. See, it's a very symmetric kind of expression. No? If you do the inverse, you'll get a log there. So the log will come from there. Okay, and the by 2 will also go away very easily, and these two expressions will work out to be exactly the same. Okay, right? Yes, everybody's okay. So, but somehow I think this expression is a little bit more exciting than this expression. You don't see anything here. I mean, where is the code here, so to speak? I mean, you literally used every code word of the code. That's what you've used here. On the other hand, in this expression, you're using a parity check condition. The only parity check condition that there is in this code you're using. Okay, and you get a very nice equation. Okay, is that okay?
Yeah.
Okay, so the next thing we're going to do is a slightly more complicated example to just show that such an idea can, I mean, you have to pay attention when you use this idea in general. Okay, so in this case, for the repetition code, it's very easy, works out very nicely. But for the other codes, for even a slightly more complex code, this equivalence is very difficult to see. Okay, so let's not equivalence. This kind of simplification is difficult to do. Okay, so let me show you one more example. Let's see how many of you see anything interesting here. Okay, so the next example we'll do. Okay, so I'm going to do a slightly tricky example. Okay, so try and stay with me here a little bit. Okay, it'll be kind of like it'll be a very simple example only, but it will be something which will not be true at the end. Okay, so don't be surprised by it. Okay, so finally we'll do something and we'll show that two things are not the same. Okay, so basically we have to pay attention is what I'll show. Okay, so think about that as we go along. Okay, so let me take a code defined by a certain parity check matrix. Okay, and I want this parity check matrix to have a very simple structure. So maybe I'll take it to be, my God, this is just, no, it's just driving me nuts. This, this constant deweeding that I have to do. Okay, so let's say we have a code. So I'm trying to see if I can get a slightly more non-trivial code, which is, so yeah, maybe I can try this. 0, and let's say, no, let me keep this 0. Okay, and then maybe I'll keep this as 0, 0, 1, 1. Okay, let me see. Let me think about this for a while. Should we? Okay, so we'll keep this code. So okay, this is a good enough code. The code from this is quite easy, right? Okay, we have seen this before. What is the code? This is a parity check matrix. Which is the code?
All one.
Okay, so you have, this is one of those self dual codes, right? So maybe this is not so interesting. No, maybe I should change this a little bit. So how can I? Okay, so let's just keep it like this. It's okay. We'll keep it like this. So if you compute L1 directly, what do you get? Capital L1. You would get small L1 plus log e power L2 plus L3 plus L4 plus e power L2 divided by e power L3 plus L4 plus 1. Is that okay? Okay. So now you might want to argue that the conditions imposed by the parity check matrix, or what are the conditions imposed by the parity check matrix? C1 XOR C2 equals 0, and then C3 XOR C4. Yeah, you can do further things. Well, this is kind of two codes put together, so that's why it's like that. So that's another reason why that happens. Anyway, let's not worry about that. So let's keep this. Okay. So suppose I want to repeat this. Maybe this will work. Let me see. This is a simple enough example. Maybe it will work. Let's see. Suppose I want to repeat the previous argument. What is it that I should do? Capital L1 plus. Okay, so let's go back. So I want to look at capital L1. So it's going to be small l1 plus 2 tan h inverse of what? It's just C2, right? So it will be just L2.
Oh, okay.
And then what do you do?
That's it.
Okay, so if you say that's it, then that's wrong clearly, right? I mean, you won't get the expression that you have here. Okay, what is missing in this?
We'll get it, sir.
Because if you take e power L2 common, then e power L3 plus L4 will cancel each other. So
Okay.
eventually that
So then this is not a good example. Okay, so anyway, so that's fine. We got it. Okay, so this works out to L1 plus L2, which is the same as this. Okay, so in this example, maybe it's good. So okay, so let me change this example slightly. Okay, so I should change this example. So if I do the following, say for instance, if I do something very similar to that, so that's why I think I was not very confident of the previous code. It was not a good example. So suppose I change this. Okay, I put a 1 here. Okay, so let's do this. This is a little bit more tricky. Okay, so the code in this case becomes what? It goes all zeros, and then what? One one zero zero is not a code word. 0011. Okay, what else? 1110, yeah, that is there, and then 1101, that's also there. Okay, so those are the 4 code words in this code. Okay, so let's try the same trick as before. Let's see if it works. Capital L1 is going to be small l1 plus log e power. The first term is always going to be there. Okay, L2 plus L3 plus L4, and then the next term is going to be e power L2. There's no change here, but the denominator changes. Denominator becomes e power L4 plus e power L3. Okay, so now it won't work, I think. We'll see. Okay, so you'll see there's a way to fix it. I'll also show you the way to fix it. Okay, so you'll see that you have to pay attention with this independence stuff. You have to be very careful with what the dual code means. Okay. So once again, let's see if we get carried away and we say C is the set of all code words C. It's not getting carried away. It's very true. C1 XOR C2 is 0, and then C2 XOR C3 XOR C4 is 0. Okay, and if you want to do capital L1, you're going to say small l1 plus small l2 and kind of stop there, and clearly this is not true. Okay, what did we miss? Yeah, so there is some implied dependence between through C2, right? See, C1 depends on C2, and then you are saying C2, C3, C4 depends, but actually C1 also through C2 depends on C3 and C4. Okay, so it turns out this linear independence, which is kind of sufficient to define the entire code, does not fully capture the statistical independence between the code word bits. Okay, so just because you have a set of linearly independent vectors, you can't just stop there. Okay, you have to take all possible linear combinations of the basis vectors and take every single parity check that comes from every single check, okay, because linear independence, what does it got to do with statistical independence? Okay, you might still have dependence through that. For instance, there is one more code word here in the dual. What are the 4 code words in the dual? 0 0 0 0, 1 1 0 0, 0 1 1 1. What is the other code word in the dual? 1 0 1 1, right? 1 0 1 1 is another code word in the dual. Okay, so in the definition of my code, I really do not have to write that. I do not have to really write C1 XOR C3 XOR C4 equal to 0, because anyway linear independence implies that is true, it will not give me any new condition. But when I write statistical independent assumptions like this, you have to account for this guy also. Okay, you can't just generally ignore that one. Okay, so C1 plus C2 is 0, and you also have C1 XOR C3 XOR C4 equals 0. So clearly R2 will tell me something about C1, and R3 and R4 also tells me something about C1. Okay, I can't just stop that based on linear independence. I have to look at every single dual code word and collect all the information that is coming through from these things. But luckily here, the way this thing has worked out, the extrinsic information I get from this equation is statistically independent of the extrinsic information I get from this. Why is that? Because R2 is involved here and R2 is not involved there. So that is only R3 and R4. So I can clearly add, there is no problem, add the log likelihood ratios or multiply the probabilities, I can do that. Okay. So if I add the third one also, I should get this expression, the original expression. Will I get that? Yeah, I will get that. Right. So you can write 2 tan inverse, tan hyperbolic inverse. Yeah, so you can do that and you will see that will agree with the expression that we had. You will see these two guys agree, they are okay. Is that okay? Okay. But nevertheless, I want to point out one thing to you. Okay. If you want to simplify complexity, okay, here it is not really any simplification of complexity, there are only 4 guys here, you can probably stop here. You know, I have only so many parity checks at hand, okay. I will only compute whatever it is that I know about my first bit using only these parity checks. Okay. If I want to refine it further, what will I do? I will add more parity checks and see if that gives me something more independent. Okay. So this is a crucial idea, even though it comes like a burden to you, right, it is one more term which you have to account for. It is a crucial idea in suboptimal soft decoders. Okay. You look at as many parity checks as you can handle, okay, so and then you compute it and then try and incrementally add additional parity checks. But the only crucial thing is, if there is this independence that holds, then it is very easy to add the new information that is coming in. However, if this independence does not hold, you do not know how to combine really. Okay. So guess what people will do in approximate soft decoders? They will assume it is independent even if it is dependent and keep adding. Okay. So hopefully this silly exercise we are doing with these computations is telling you something at a high level. Okay. The important idea that I am trying to convey here is, you can look at the bitwise MAP expression from the dual code point of view. Okay. Every parity check that you have, not necessarily linearly independent ones, even the linearly dependent parity checks can give you additional extrinsic information about the particular bit. The only condition is that bit should be involved in that parity check. Okay. Of course, if you have C2, C3, C4 is 0, it is not going to tell you anything about C1. But the bit itself should be involved in the parity check. Every time the bit is involved in the parity check, you get some additional information. If it is independent, then it is very easy to account for. You simply keep adding everything you get. If it is not independent, then it is difficult in general, but one approximate thing to do is to simply assume independence and add. Okay. And how do you check for independence between 2 different parity checks? They should not have any other received value in common. They can have of course C1 in common, they will have C1 in common, but nothing else should be common. If it is not common, then definitely it is independent. But if it is common, then it is not independent, but in a suboptimal decoder you might want to assume independence and keep adding and see what happens. Okay, that is the idea. So I want to show you one example where it will not be independent, but when you add, maybe you will get some expression which looks reasonably close. Okay, so who knows. Okay, so let me try and cook up that example. It is a little bit more difficult to come up with that example. So let us see. H what can we do for this example? Okay, let us try this. Will this work? Does this work? No, actually it won't work, you know. So let us keep it like this, let us keep it like this, let us keep it like this. Maybe this gives us something interesting to ponder about. Okay, see, this actually is very equivalent to 1100 0011. Okay, and you work with this parity check and everything seems to work fine, but if you directly work with this one also, it might actually work. No, so maybe this is not a good example. Okay, so maybe. Yeah, maybe you need more rows, and that's not a, that's too painful. So maybe I'll erase one column. What will happen if I do this? Yeah, third column is always 0. Okay, so maybe it is not a good example. Okay, but I want to give an example where you have dependence. So maybe we will take a larger example and then we will do it approximate only. Let us not do the optimal thing, we will just do the approximate thing and then see what happens. Okay, so let us take a slightly larger example. Okay, so this is a bit painful. So let us try this 111, let me try 00. Okay, so we will try 5 columns and then let us try this. Okay, let us try this, I mean let us see where it goes. Okay, so maybe let us just try this. Okay, so it is painful code. It has just 4 code words again, right. So it is not so difficult to write this code down. Okay, so what will be this code? Okay, the all 0 code word code, then 11. This one is a code word. 10101. Okay, then what about okay 01110. Okay, so that is correct. Those are the 4 code words. So if you want to write capital L1, actually this is a bad example because the code itself has only 4 code words and you are trying to go to the dual code which has 8 code words. So maybe it is not a good example. Okay, but anyway, so let's see this just to make sure that you have to be careful when there is dependence. Okay, so the expression might be totally different between the actual answer you would get and the wrong answer you get by assuming independence. Okay, so I want to show that. Okay, so L1 is quite simple here, small L1 plus log e power L2 plus L3 plus L4 plus L5 plus you will have only one other guy which will be e power L5. Am I right? And then in the denominator you are going to have e power L3 plus e power L2 plus L4. Okay. So by now I think enough people must be getting enough experience with writing these expressions down. It's quite easy, right? It's not very difficult. Just look at it and you can write it down. Okay. So now if you were to try our approach, the initial cut of our approach, the first approach would be is to do capital L1 equals small l1 plus look at the first parity check. Okay. That first parity check is going to give you something involving L2 and L3, am I right? So, it is going to be the 2 tan hyperbolic inverse. Okay. So, if you were to do the first parity check, it is going to be tan hyperbolic L2 by 2 tan hyperbolic L3 by 2. Okay, so this is an okay approximation. Okay, so let me put approximate. Okay, so clearly it is not equal. So it is an okay approximation, but you might want to say start with the second row instead of starting with the first row. Then instead of L2 and L3, you will have L3 and L4, or you might want to start with the last row. So I am going to argue starting with the last row is a smart thing to do. Why is starting with the last row a smart thing to do?
That's the only thing which has L5.
So
Independent.
Well, actually having a lower weight is better, you know. So think about it. If you have x equals y plus z, okay, and if you have x equals y plus z plus w, and somebody gives you probability for y, z, and w, you have to compute probability for x. You have 3 different things. You have added all up, the value will go down. So it's only heuristic, but think about why it works. But if you have only 2 things, then you get a better probability. Okay. So anyway, so that's a heuristic. Anyway, it's good to think about that. Of course, it depends on the actual received values also, but the heuristic is to go for the lower weight vectors first, okay, because that gives you really good information which you won't get from the larger weight vectors. See, as you keep on XORing bits, they will tend to equally likely bits, right? You take for instance n bits, each likely to be 0 or 1 with probability, let's say 0.1. But when you XOR all of them together, the probability will become very close to half, because it will be 1 minus p raised to the power something divided by 2. Okay, you can check that out. Okay, so as you XOR more and more bits, you will come closer and closer to 0.5, which is very bad. You know, I mean, so 0.5 probability is not so good. So you have to go for lower weight code words in the dual. Okay, so now the second row is really difficult to account for. Okay, and if you assume independence there, you will get something involving L3 and L4, and the third row is easy to account for, because that is going to be independent, and you get L5 out. Okay, and you see even here e power L5 comes out, and you get L5 plus something involving L2, L3 and L4. Okay, but this summation is clearly different from that function of L2, L3 and L4. Okay, and it is not very easy to approximate it that way also. It may not even be a good approximation. Okay, you may not be able to do it, and the only way to do that is to actually look at the original code. I mean, you have to really undo all the dependencies. Without undoing the dependencies is tough to approximate. Okay, a good exercise is to actually write this down, simplify it, and see how different it is from the other thing. Okay, you will see there are a lot of things. In fact, there is one more code word in the dual which also has the 1 in the first position. Okay, which is what, the XOR of all 3, 1 1 0 1 1, that is also in the dual. Okay, see, this is also a valid dual code word, right? It is the XOR of all the 3. Okay, for this also you will get one more contribution, and how do you account for that? That is also tough. You can't just add. Okay, adding is tough because it involves both L2 and L4 and L5, and it is totally dependent on the previous things. Okay, you have to undo the dependency there. You can't do this very easily. Is that okay? So this is my example, a bad example where things don't work out. Okay, the previous examples things worked out. Okay. Yes.
Anything like alternatization and then adding the extra information we got from some other. Generally, what we do in adaptive
What do you do? I mean, I don't know what you do in adaptive signal processing, frankly. Okay, so the question was, is there any connection between these things and other areas in general? Okay, so there are huge connections, of course. I mean, so signal processing and these kind of approximate soft ideas, lots of connections, and in a starting course, I mean, it's absolutely no time to look at all those things. Okay, so anyway, so what I want to convey with these examples, I mean, I have done it mostly by example because it is difficult to do any theory here. Okay, it's all approximate and mostly heuristic. The basic idea is, instead of thinking about the bitwise MAP expression in terms of the original code words, you think about them using the dual code words. Every parity check you have or every code word in the dual which has a 1 in the position you want, for instance in C1, that will be involved in the bitwise MAP expression. It has to be involved, somehow you have to make it involved. As long as the parity checks are independent, as in they do not have any common received values, you can happily add the log likelihood ratios. Whenever they start having some bits in common, you run into trouble, you really cannot do anything. One approximate thing is to simply assume independence and add, and that is the standard method that is used in almost all suboptimal soft decoders, okay, and it really works quite well, okay, without too much of a problem in practice. Okay.
Regions outside the union bound.
Okay. What is the question? I'm sorry. The question is about how this relates to the union bound. Okay, I don't know if there's
maximum extrinsic information we can get even if we add all the things.
well, it's okay. So the question is basically, is there a way to analyze these things? There's really no good way to analyze these things. Okay, once you bring in the dependence, it's difficult to analyze. Okay, so we will see some analysis assuming independence, but not assuming with the dependence in the picture. Okay, so to summarize in the couple of minutes that we have, we want to move from optimal decoders, optimal soft decoders, to suboptimal soft decoders. And the crucial thing here is the parity check matrix. Okay, so parity check matrix is used in one specific type of suboptimal decoders, but that is the kind that I will be talking about mostly. So, the parity check matrix plays a big role, okay. Not just the parity check matrix, but also linear combinations of the rows of the parity check matrix also matter. Okay, so how they interact with, how they overlap with each other kind of plays a role in this. Okay, so all this, it turns out, is nice and easy for the bitwise MAP decoder, and I should confess that I really do not know if such a method exists for the ML decoder. Okay, so I do not know, I mean maybe there is, but I have not educated myself on it, but I think that there should exist, but maybe the language is a little bit more difficult, maybe some trellis is involved and some Viterbi decoding, etc. is involved, but it is not as simple as the bitwise MAP decoder. Okay, so that is why I said the bitwise MAP decoder is it's much more popular in the soft decoding idea than ML decoders. Okay, so people use bitwise MAP and it works out okay. All right, so we'll stop here with this lecture. We'll take a break and continue